Welcome back. Last time, we solved the voltage divider bias circuit the honest way, the exact way, with Thévenin, and we ended on a striking number, half a milliamp poured down the divider ladder, while the base sipped only 6 microamps through it, 85 to 1. A sip that small does not move a river. Today, we cash that in. If the base current is truly negligible, why carry it at all? Drop it, and the whole Thévenin detour collapses into 3 short lines. But there is a condition, and an engineer always checks the condition before taking the shortcut. So let us start there. Here is the same circuit, and here is the question we must ask first. Is the divider stiff enough? Think about what holds the base voltage. The divider tries to fix it at one value. The transistor leg, pulling current through the emitter, tries to load it down. The emitter resistor, seen from the base, looks like beta plus 1 times R sub E, the reflected resistance we met last time. The base node stays firm only if that reflected resistance is much bigger than the lower divider resistor R2. The standard rule of thumb, beta times R sub E should be at least 10 times R2. Let us test it. Beta times R sub E is 140 times 1.5 K, which is 210 K. 10 times R2 is 10 times 3.9 K, which is 39 K. 210 K is comfortably bigger than 39 K, more than 5 times over. The divider is stiff. The criterion passes, so we are clear to ignore the base current. Everything that follows rides on this one green light. Step 1. The base voltage, in a single line. Because we are now treating the base current as 0, no current branches off into the transistor. The divider is unloaded. So the same current flows straight down through R1 and R2, and the base just reads the voltage at their junction. That is, the plain voltage directory rule you have known since the very first resistor lesson. The current down the ladder is the supply over the total resistance, 22 volts over 42.9 K, which is 0.5128 milliamps. The base sits at that current times R2, 0.5128 times 3.9 K, which is almost exactly 2 volts. V sub B equals 2 volts. No Thévenin equivalent, no base loop, no reflected resistance. One divider, one line. Step 2. The collector current, and watch what is missing. We know the base sits at 2 volts. Cross the base emitter junction, drop the usual 0.7, and the emitter sits at 2 minus 0.7, which is 1.3 volts. That voltage sits across the emitter resistor, and Ohm's law hands us the emitter current directly. 1.3 volts over 1.5 K, which is 0.867 milliamps. And as always, the collector current is essentially the same. I sub C is approximately 0.867 milliamps. Now look back at what we just did and notice what never appeared. Beta, we never used it, not once. In the exact method, beta sat in the denominator and nudged the answer a little. Here it is gone completely. The base voltage is set by 2 resistors and the supply. The current is set by that voltage and the emitter resistor. The transistor's gain has no say at all. Swap in a part with beta 50 or beta 300 and this circuit lands on the very same operating point. That is why the source crossed beta out. Step 3. The collector-emitter voltage, the last unknown. Walk the output loop, exactly as before. Start at 22 volts, down through R sub C carrying I sub C across the transistor, and down through R sub E carrying I sub E. The collector resistor drops 10K times 0.867 milliamps, which is 8.67 volts. The emitter resistor drops 1.5K times 0.867 milliamps, which is 1.3 volts. So V sub CE is 22 minus 8.67 minus 1.3, which is 12.03 volts. Quick sanity check. The 3 drops should rebuild the supply. 8.67 plus 12.03 plus 1.3 is 22 volts, exactly. Nothing leaked. 3 lines and the circuit is solved. Now the moment of truth. Was the shortcut honest? Let us lay today's approximate answers beside last time's exact ones, side by side. The base voltage, exact, gave 1.98 volts, approximate gave 2.00. The collector current, exact 0.846 milliamps, approximate 0.867. The collector emitter voltage, exact 12.26 volts, approximate 12.03. Every pair agrees to within about 2%. 2% for a method that skipped an entire Thévenin construction and never touched beta. That is the engineer's bargain. When the divider is stiff, the exact answer and the quick answer are practically the same number, so you take the quick one. If the criterion had failed, if the divider were soft, the gap would widen and you would go back to the exact method. The criterion is what tells you which world you are in. Let us pocket it. The approximate voltage directory method is 3 lines. Check the criterion. Beta R sub E at least 10 times R2. If it passes, ignore the base current. The base voltage is just the divider, 2 volts here. Subtract 0.7 for the junction, divide by the emitter resistor, and you have the current, 0.867 milliamps. One output loop gives the collector emitter voltage, 12.03 volts, and the headline you carry forward. In a stiff divider, the operating point does not depend on beta at all. That is the whole reason this is the bias circuit real designs reach for. You solder in any transistor from the bin, and every board lands on the same point. With this, our DC analysis of the BJT is complete. Fixed bias, emitter bias, and now voltage divider bias, exact and approximate. Next, we meet a different kind of transistor, the field effect transistor, where a voltage, not a current, is in command. See you there.